In the area of science and gigantic mysteries, the subject of what existed previously to the gigantic explosion has blended conversations and intrigued characters for quite a while. This huge question doesn't just test how we could decipher the universe, it challenges the genuine furthest limits of human knowledge. Imagine standing at the edge of existence, looking into the colossal shadowing and pondering what lay there before our universe was imagined. The event of the Big Bang marked the beginning of time, space, and all that we know. But were you there a moment earlier? Previously? Could there have been a condition of nothingness, a calm before the cosmic gathering began? And if this is true, was it? Or perhaps was there something much more alarming that existed previously, before time itself? As we dive further into this question, science takes us on a journey past the universe's beginning point into thoughts that challenge our consciousness. Physicist Brian Cox, known for his investigation into the wonder of the universe, suggests that something surprising might have existed before the enormous detonation. He challenges us to reconsider our understanding of reality and existence. In this examination, we'll dissect the science, the speculation, and the dazzling secrets that might explain what existed before everything. We'll explore thoughts like self-important development, quantum changes, dark energy, and even multiverse. The answers we reveal might just paralyze you, yet they could also open up new perspectives on our place in the universe. Get ready to dive deep into a realm that defies imagination and science, where the obscure still wins around the shadows, leaving scientists flawed and sometimes even upset. We ought to explore what existed before the Big Bang, and why these theories challenge everything we thought we knew. To appreciate what may have existed before the Big Bang, we first need to painstakingly analyze what the Big Bang truly was. The Big Bang, as scientists define it, refers to the moment when the universe became extremely hot and dense, growing rapidly to trigger the development of all matter, energy, and forces. When we look toward the night sky, we see evidence of this hot beginning, with galaxies spreading out from an early starting point. But for what purpose did this happen? Was there a period before this dense, hot start? According to the theory of cosmic inflation, there was unquestionably a time before, and it was not even close to void or peaceful. Vast expansion suggests that before the Big Bang, the universe was in a state that was cold, empty, and loose, essentially like an immense vacuum. However, this vacuum wasn't entirely empty, it contained a gigantic amount of energy that fueled the rapid expansion of space itself. This expansion, called inflation, happened so rapidly that it essentially established the groundwork for everything that would follow. A portion of space expanded at unfathomable rates until the expansion slowed down, and the energy transformed into matter, particles, and the forces we see as the Big Bang. But what was the nature of this energy? Why did it suddenly grow the universe? And why did it stop? Specialists believe that this immense expansion created patches of the universe, each experiencing its own Big Bang. Imagine a fabric extending endlessly, with minuscule air pockets forming here and there, each air pocket representing a universe, including our own. This idea, called the inflationary multiverse, suggests that there are possibly limitless Big Bangs, and an infinite number of universes. Our own is just one of many. This huge, mind-bending reality challenges our understanding of the very universe itself and leaves us with the question, what else is out there? The idea of nothingness before the Big Bang is speculative, not real, at least as per our current understanding. Regardless of whether you eliminate all energy, particles, and radiation from the universe, it would still not be truly empty. Darkness fills the void in our universe. Matter, dark energy, quantum fields, and other forces weave an inevitable tapestry of something, even in its most vacant form. Even if we imagine stripping away all of these forces, leaving a dead space, the universe would still generate new kinds of energy. This reality alone is bewildering to specialists, as it suggests that true nothingness might be impossible within our infinite comprehension. Space itself has properties, rules, and constants that prevent it from being totally empty. Imagine creating a region with literally nothing in it, no particles, no radiation, and no energy, except quantum fields and major constants. These would still exist, suggesting that this nothingness has properties. For instance, there's a peculiarity called zero-point energy, which represents the least possible energy condition of quantum fields. In this state, particles can still momentarily appear and vanish, creating a ghostly resonance of movement, even in what should be empty space. This challenges our idea of a real void and suggests that, yes, even before the Big Bang, there was something scientists are only beginning to understand. One of the most astounding theories in modern cosmology is the possibility of timeless inflation. If inflation could cause our universe to exist, it's possible it could continue forever. Brian Cox describes an astonishingly vast inflationary multiverse where universes are infinitely created and continue expanding. Imagine each Big Bang as a flash lighting another universe, while inflation continues in different areas, making countless other universes. This cycle could, in theory, go on for eternity. This idea of vast universes gives birth to an enchanting concept of a fractal universe, where each new universe might actually create its own Big Bang. Every universe exists as a separate, independent domain, unaffected by the others because of the rapid expansion of space. This hypothesis, for researchers, is both exciting and upsetting, as it suggests a never-ending multiverse with no definitive beginning or end. Imagine our universe being just one bit in a giant cosmic structure, forever expanding and constantly creating new universes. And what if the disturbing reality is that there is no before or after, but rather a timeless pattern of universes forming and decaying? How we interpret nothingness changes when we consider quantum field theory. According to this theory, the universe is not just an assortment of matter floating in space, rather, it's a complex network of energy fields that fill the universe, connecting to create everything we observe. These fields are like invisible seas, with particles acting as disturbances or waves. Even when fields are at their lowest energy level, known as the vacuum state, they are still active. Particles can appear and disappear in these fields, momentarily borrowing energy before returning it. This phenomenon results in virtual particles, substances that immediately exist and then vanish, leaving only a faint memory of their presence. The idea of virtual particles challenges the concept of a real void. Imagine an empty universe where all matter, radiation, and energy are removed. Would you have total nothingness? According to quantum field theory, you wouldn't. Even in a vacuum, fields remain active, sometimes creating transient particles. This constant movement in what should be nothing suggests that the universe doesn't recognize our concept of emptiness. The fields and forces endure, filling the universe with a hidden energy. As it might not only reveal the truth about our universe's origin but also offer evidence of what existed before the Big Bang itself. These waves would act like fingerprints, carrying imprints of the cosmic conditions that predated our known universe. If we could detect them, we might finally glimpse the very physics that govern the pre-Big Bang era, perhaps even confirming the existence of a multiverse, a previous universe, or unknown fields that shaped everything we are. But there's more. Theories rooted in string theory and loop quantum cosmology also offer radical insights. According to string theory, all matter and forces arise from vibrating strings of energy, and these vibrations may occur in higher dimensional spaces. In this view, our universe might be a three-dimensional brain floating in a higher dimensional bulk. A collision between such brands could have triggered what we experience as the Big Bang, meaning, the event wasn't a beginning, but rather a transitional moment between phases or dimensions. Loop quantum cosmology, on the other hand, proposes that time and space are quantized, made of discrete units. According to this idea, the Big Bang wasn't a singularity, but a bounce from a previous contracting universe. This theory replaces the infinite densities of classical Big Bang models with a minimum possible volume, meaning, there was a universe before ours, which collapsed and rebounded into what we now inhabit. Each of these theories, multiverse, quantum fields, dark energy remnants, brain collisions, or cyclical rebirth, paints a picture of a cosmos that is far grander, older, and more mysterious than previously imagined. None of them confirm an ultimate beginning. Instead, they challenge us to rethink time, existence, and what it means for something to begin or end. What lies before the Big Bang might never be fully known, but every step toward understanding takes us deeper into the architecture of reality. Whether through the detection of gravitational echoes, the mapping of cosmic microwave background patterns, or the mathematical beauty of unified field theories, science continues to push the frontier. In the end, the mystery of what existed before the Big Bang may not just be a scientific question, but a philosophical one, a meditation on existence itself. And perhaps, as we reach further into the unknown, we're not just uncovering the history of the universe, we're discovering our place within a much vaster, timeless reality. About the Big Bang, but also offering a glimpse into the cosmic state before our universe was born, this theory presents a tantalizing prospect, detecting gravitational waves that could act as fingerprints of a pre-Big Bang universe. As we continue to explore what could have existed before the Big Bang, we delve into concepts that push the boundaries of our understanding, challenging even our most fundamental assumptions about space, time, and existence itself. One of the most mind-boggling ideas comes from the realm of the study of quantum gravity, which aims to merge quantum mechanics with general relativity. This merger could potentially reveal a unified theory of everything and might offer insight into what existed before the Big Bang. Quantum gravity suggests that space and time are not smooth, continuous entities. Rather than experiencing them as seamless, they may instead have granular structures. This theory posits that the fabric of spacetime itself could have originated from a microscopic Planck-scale structure, with tiny quantum fluctuations shaping the universe in ways we cannot yet fully comprehend. In this view, what we perceive as the smooth continuum of space and time might have only emerged from these changing quantum fields. The state before the Big Bang could be described by a radically different concept of reality, one where space and time themselves were not fully formed. Another possibility is that the universe is part of a vast cosmic landscape of possible universes, each with different physical laws and constants. This theory, known as the string landscape, arises from string theory, which suggests that all fundamental particles are actually tiny vibrating strings. In this framework, there are many possible configurations of these strings, each corresponding to a different set of physical laws. The string landscape might suggest that our universe is just one of many, each emerging from its own distinct Big Bang-like event. The existence of such a landscape also brings forth the notion that other universes might have different dimensions, different strengths of gravity, or even various kinds of matter. In this view, our universe might not be unique but rather part of a multiverse, a collection of universes, each evolving independently. The multiverse theory provides a speculative yet fascinating answer to the question of what came before the Big Bang, another universe, in a different configuration, potentially leading to infinite cycles of creation and destruction with no definitive origin. In addition to these theories, some physicists have also considered the role of black holes in shaping the nature of the universe. A hypothesis gaining attention is that our universe could be the result of a black hole formed in another universe. In this scenario, the singularity at the center of a black hole could be a way to get to another universe, with the Big Bang being the moment when such a black hole gave birth to our cosmos. This hypothesis is bolstered by the fact that, as per general relativity, the singularity at the center of a black hole is a point where space and time curve infinitely, creating a region where the known laws of physics break down. It's possible that the extreme conditions inside black holes could lead to the creation of new universes, which may suggest that what we consider the Big Bang was just the birth of our universe from the singularity of an ancient black hole. Exploring these concepts necessitates a thorough investigation of time itself and its very nature. Some cosmologists speculate that time as we understand it may have had no meaning before the Big Bang. If time began with the Big Bang, then there may have been no before in any conventional sense. According to this view, time itself might have emerged from a quantum fluctuation or from a primordial state where the usual distinctions between past, present, and future did not apply. This could lead us to rethink the concept of causality, which relies on the assumption that events happen in a linear sequence. If time did not exist in the way we experience it, then the question of what preceded the Big Bang becomes nonsensical, as there would be no temporal framework to support it. Further complicating the picture are theories of cyclic time. As mentioned previously, cyclic cosmology suggests that the universe undergoes endless cycles of birth, evolution, and eventual collapse. In this model, the Big Bang could represent just the most recent bounce in an eternal series of universe cycles. These cycles might not be the same, but they might evolve in different directions, each with unique physical properties. The cycle of the universe, according to this theory, would be a continual process with no true beginning or end, rendering the question of before the Big Bang meaningless in the conventional sense. The idea that time itself might be cyclical implies that each and every Big Bang could be followed by a contraction and another big crunch, with the universe reinitiating itself in an endless loop. A different avenue of inquiry into the potential of the cosmos is its primordial state, a soup of particles and fields that existed prior to the formation of stars and galaxies. This concept suggests that before the universe began its rapid expansion, it was filled with a dense and hot mixture of elementary particles, including quarks, leptons, and bosons, all in a state of extreme energy. These particles would have been interacting at very high temperatures and densities, laying the groundwork for the formation of matter and energy. As the universe cooled, some versions of this theory suggest that this primordial soup existed in a quantum foam, where particles constantly emerged and vanished due to the uncertainty principle of quantum mechanics. The soup's properties could potentially offer insights into the earliest moments of the universe and, by extension, what preceded the Big Bang itself. Ultimately, what existed before the Big Bang remains one of the most profound mysteries in science. As our understanding of quantum mechanics, cosmology, and fundamental physics deepens, new theories will continue to emerge, offering increasingly complex and occasionally paradoxical explanations for the origins of our universe. While we may never fully grasp what came before the Big Bang, the pursuit of this knowledge will continue to push the boundaries of human curiosity, driving us to explore the unknown frontiers of existence. This journey toward understanding what came before the Big Bang is not just a scientific endeavor, it is deeply philosophical. It forces us to confront questions about the nature of existence, the limits of human perception, and the role of consciousness in interpreting reality. Are we capable of fully comprehending a universe, or multiverse, that may exist beyond our observational reach? Or are there inherent limits to what we can know, dictated by the very structure of the cosmos? Some physicists argue that certain aspects of pre-Big Bang conditions may forever remain inaccessible, hidden behind a veil of observational constraints. For example, if time itself was born with the Big Bang, then any effort to peer beyond it might be akin to asking what lies north of the North Pole, an ill-defined question rooted in the wrong assumptions. Nevertheless, this has not stopped theorists from attempting to construct mathematical models that push past this boundary. Loop quantum cosmology, for instance, is one such framework that proposes a quantum bounce instead of a singular Big Bang. According to this model, the universe didn't emerge from nothing, but rather from the collapse of a previous universe, which then rebounded into expansion. In this picture, the Big Bang is not a beginning but a transition, a phase change from one cosmic state to another. Such models challenge the traditional narrative of a singular origin and instead paint a picture of a cyclical or even eternal cosmos, evolving through infinite iterations. In parallel, advancements in observational astrophysics are opening new windows into these early moments. Instruments like the James Webb Space Telescope and gravitational wave detectors such as LIGO and Virgo are enabling scientists to gather data from deeper in time than ever before. Though they may not capture a direct image of what preceded the Big Bang, they can reveal subtle imprints, such as cosmic microwave background anomalies or primordial gravitational waves, that hint at physics beyond the standard cosmological model. Even the concept of a multiverse, once relegated to the realm of science fiction, is gaining traction within serious theoretical circles. Inflationary cosmology, a well-supported theory explaining the rapid expansion of the early universe, naturally leads to the idea of eternal inflation, where inflation never completely ends but spawns an infinite number of bubble universes, each with its own distinct laws of physics. Ours would be just one such bubble, lucky, perhaps, to have the precise conditions for life. But this proliferation of theories brings with it a profound challenge: falsifiability. If other universes are fundamentally unobservable, can their existence be tested, or are they metaphysical constructs beyond the domain of empirical science? This tension between bold theoretical exploration and rigorous scientific validation is at the heart of modern cosmology. Yet, even amid uncertainty, there is purpose. The very act of asking what came before the Big Bang expands our intellectual horizons. It pushes us to develop new mathematics, new physics, and new ways of thinking. Whether we ultimately discover a definitive answer or not, the pursuit itself may reshape how we view reality, revealing that our universe, and perhaps existence itself, is far stranger and more beautiful than we ever imagined.